Hello and welcome to Physics 2212 Lab 1. The purpose of this lab was to determine the electrostatic interactions between charged pieces of tape with other objects, and was also to investigate the excess charges or deficient charges present on one piece of tape and to compare the physical system with a computational model in GlowScript. Starting off with some key principles, Newton's second law states that the force is given by mass times acceleration. This can be extended to the gravitational force, where force is given by mass times the acceleration due to gravity, which is 9.8 meters per second on the surface of the Earth. Then we have Coulomb's law, which states that the charge between two charged particles is given by the following formula, where Q1 and Q2 represent the charges of two particles, and R is the vector pointing from the source charge to the charged particle being acted upon. K is Coulomb's constant, given by 9 times 10 to the 9 Newton meters squared per Coulomb squared. We then modeled the charged tapes as point charges to investigate the electrostatic forces between the two charged tapes. Several key assumptions were that the charge was concentrated at the center of each tape. We also assumed that each tape had the same amount of charge evenly distributed along the length of the tape. For a brief preview of the results, it was determined that the charge on each piece of tape was 3.63 times 10 to the minus 9 coulombs, and that the amount of electrons lost by each tape was 2.27 times 10 to the negative 10 electrons. It was then calculated that the fraction of electrons lost was 126 times 10 to the minus 9. The dimensions of the tape are shown here, with the suspended tape having a mass of 0.1 grams. One charged tape was suspended off the table whilst the second charged tape was held underneath. The separation distance required to levitate the suspended tape was then measured at 1.1 centimeters. Here, the system is defined as the suspended tape, whilst we define the surroundings as the held tape and everything else. The weight force was calculated using W equals to mg. This was then equated with the electrostatic force as demonstrated using the free body diagram, where the electrostatic and weight force directly oppose each other. We use the assumption that the charges of both tapes are equal to Q, and then by rearranging the equation to solve for Q, we calculate the charge to be 3.63 times 10 to the minus 9 coulombs. To calculate the fraction of atoms that gave up electrons, we first divide the area of the tape by the area of each atom. This gave us 1.8 times 10 to the 17 atoms. Next, the number of electrons was calculated by dividing the total charge on the tape by the charge on an electron, which gave 2.27 times 10 to the 10 electrons. And since this charge on the tape was positively charged, that means 2.27 times 10 to the 10 electrons were deficient on the tape. We then divide the number of electrons deficient by the total number of atoms to get the fraction of atoms that gave up electrons. This comes out at 126 times 10 to the minus 9. For the computational model, we start by first establishing all the constant and initial parameters in the experiment, such as mass of the tape and its length. We then initialize the tapes as spheres and calculate the weight force acting on tape B. We can then solve for the amount of charge required to levitate tape B on top of tape A. From this, we are able to calculate the number of electrons by dividing total charge by the charge on a single electron. Next, we calculate the electric field acting on B due to A, showing the E field function. From this, we multiply by the charge on tape B to calculate the electrostatic force acting on B due to A. The outputs are shown here, where the gravitational force and electric force equally oppose each other. Here, we have calculated the charge on the piece of tape to be 3.63 times 10 to the minus 19 coulombs. All other calculations give the same results as calculated for our physical system. Both the computational model and physical system gave the same results as expected. However, possible sources of error include inaccurate measurements of tape length, width, and separation distance. This would lead to inaccurate calculations of charge and electrostatic forces. The U-tape may not have been held parallel to the suspended tape, which would lead to an inaccurate separation distance measurement. Finally, any excessive handling of the tape would have led to the tape becoming more neutrally charged. This would lead to different magnitudes of charges on each tape. If electrons had positive charges and protons had negative charges, the electric fields for the objects in this experiment would change direction. However, since the U-tapes would then have negative charge, they would still repel each other. Thus, the observations would remain the same. Similarly, the charged pen would have a positive charge which would be attracted to the negatively charged U tapes. It's important to handle charged tapes as little as possible, as charges can be transferred between objects that are in contact with one another. Excessive handling with your hands can result in a transfer of electrons from your hand to the charged tapes, decreasing the overall positive charge of the tapes.